We want to take a look at solving logarithmic equations using the inverse property. We have a couple of examples here. Taking a look first, we want to solve the equation 5 log of 2x is equal to 10. Now when we're solving logarithmic equations, in order to use the inverse property, first we need to isolate that logarithm. I have 5 times the logarithm of something. I'd like to have the logarithm by itself, so I can simply divide by 5 first. Dividing both sides of this equation by 5, I have 5 log of 2x is equal to 10. Dividing both sides by 5, we're going to have the log of 2x equal to 2. Now we've isolated that logarithm by itself. Now we're going to take advantage and exponentiate. Big fancy talk for, we're going to write the left and the right hand side of this as an exponent. The thing to keep in mind is we have that log function. We don't see the base, but it is there. Logarithm by itself is base 10. So when we exponentiate, we will have 10 with the exponent log base 10 of 2x equal to 10 with an exponent of 2. So the logarithm became the exponent for the number 10. The 2 on the right side of the equation became the exponent for the number 10. And we use the number 10 as the base because we had log, that is the base 10 logarithm. This is where we can now take advantage of our inverse property. A log base a of x is x. So here our base 10 and our logarithm are also base 10. Those are inverses. I will be left with just the 2x. 10 to the second power is 100. So what we've essentially done is written the logarithm by itself on one side of the equation so that then we could take a base, raise it to that power. 10 to the log base 10, those are inverses. They basically kill each other off. I'm left with 2x is equal to 10, and now we can solve the resulting equation. We can divide both sides of this equation by 2. So we have x is equal to 50. It is often helpful to check our solutions. If I look at 5 times the log of 2 times 50, is this equal to 10? Well, this would be 5 times the log of 100, and the log of 100 is the number 2. 5 times 2 is definitely 10. So that checks. We are confident that the solution to the first problem is indeed x is equal to 50. Taking a look at our second equation, we want to solve 3 times log base 2 of the quantity 2x plus 1 minus 4 is equal to 2. Same attack. We're going to start by isolating the logarithm. In this case, I'll have to take a couple of steps. First, I can add 4 to both sides. So I will have 3 times the log base 2 of the quantity 2 plus 1 is equal to 6. Now, I really don't want 3 times this log. I'd love to have the logarithm by itself. So we can divide by 3. So here we added 4. Here we divided by 3. The resulting equation now becomes log base 2 of 2x plus 1 is equal to 2. We have that logarithm isolated on one side of the equation. Now it's time to raise our exponents. So now we can exponentiate it, and we're going to use a base of 2 because it's logarithm base 2. So 2 raised to the log base 2 of 2x plus 1 is equal to 2 raised to the second. The 2 became the exponent. The logarithm became the exponent. 2, the base, and log base 2 are inverses. cancel each other out, so we will be left with 2x plus 1, the argument only. 2 to the second power is 4. Now we can solve that resulting equation. Adding 1 to both sides, subtracting 1 from both sides, we have that 2x is equal to 3, and dividing both sides by 2, we get that x is equal to 3/2. And we can go ahead and check this one. I'll let you check it on your own. 3/2 times 2 will give us a 3, plus 1 is 4. Log base 2 of 4 will be 2. 3 times 2 minus 4, that's definitely going to be equal to the number 2. Isolate the logarithm first, so that then we can raise each to an exponent. Once we have the exponents, the inverse property will give us the resulting equation. Our final example contains a natural log. So far, we've used a specific plan of attack. It's going to start by isolating that logarithm. I don't want 2 times the logarithm plus 3. We can subtract 3 from both sides first. So we're going to have 2 times the natural log of x plus 1 equal to 4. I don't want 2 times a log. I want that logarithm by itself. So I'll just divide out the 2. Now I have the natural log of x plus 1 equal to 2. That natural log is by itself. Now we can use our exponentiate. We're going to use the base e. Natural log is log base e. And keep in mind, when we are raising these values to an exponent, the base does matter. Log, we use base 10. Log base 2, we use the base of 2. Natural log, we use a base of e. So e to the natural log of x plus 1 would be equal to e to the second power. Inverse property takes care of the e and the natural log, leaving us only with that x plus 1. So x plus 1 must be equal to e to the second power. And now we can simply solve. Notice e squared and 1 cannot combine, so we will have e to the second power minus 1 as our solution. And we can always go right back in and check. If you plug in your e to the second power minus 1 into the original equation, may as well. We'll have 2 times the natural log of e to the second power minus 1 plus 1 plus 3. Notice the ones will cancel. Natural log of e to the second power is going to be the number 2. 4 plus 3 is indeed the number 7, which is what the equation said. So we are very confident that the answer is indeed e to the second power minus 1. That is the exact solution.